Okay, we're going to do a bunch of examples in this video where we change the order of integration for double integrals. So let's get to it. So this is our first example. We'll take the integral from 0 to 1 and 3x to 4x of 2x plus y cubed dy dx. So the first step when you want to change the order of integration is to draw a nice picture. So let's see what we've got. We have to recall that these are going to be our y bounds and these are going to be our x bounds, given that our dy integral is in the inside and our x integral is on the outside. Okay, so let's see what we get from our picture. So we know we're going to go from x equals 0 to x equals 1. So let's just go ahead and put that right there. And then we'll go from y equals 3x to y equals 4x. So notice those are both lines through the origin. This one has a slope of 3 and this one has a slope of 4. So let's see, we can maybe draw that in the following way. So there we have y equals 3x, and there we have y equals 4x. So here we're exaggerating the difference in their slopes, and we're also not being accurate with respect to a similar scale in the x-axis and the y-axis. And that's totally okay, because all we want to do is build a picture that's going to help us to change these bounds of integration. So let's go ahead and label this. This is y equals 3x. This is y equals 4x. Okay, great. And now notice we can bring a vertical line up here, and that's going to build our picture. So in fact, we are taking a double integral over this region, which I'll shade in blue, and we'll call this region D. Okay, great. So now if we want to change the bounds of integration, what we want to notice is that this is going to be split up into two regions in the following spot. So at this intersection point, we can split this into two regions, but notice that this intersection point is the point where x equals 1 along the line y equals 3x. So this is the point 1, 3. Great. And then another important point will be up here, this intersection point, and that's where y equals 4x goes through the point x equals 1, so that will be 1, 4. Great. So we should maybe split this up into this down here, which is D1, and this right here, which is D2. Okay, so to put this in terms of a double integral instead of an iterated integral, we're going to write this as the integral over d of 2x plus y cubed dA. So that's like our differential area component. But now we can write this as the double integral over d1 of 2x plus y cubed dA plus the double integral over d2 of 2x plus y cubed dA. Okay, great. And now our goal is to express each of those where the order has been switched. In other words, the x integral is on the inside and the y integral is on the outside. Okay, let's see if we can do that. But in order to do that, what we'll need to do is change these functions. Instead of y being a function of x, we will want x to be a function of y. So we can write this as x equals 1/3 y. And then over here, we can write this as x equals 1/4 y. Okay, great. Now let's go ahead and focus on this first integral, this d1 integral. So this is going to be equal to the iterated integral of 2x plus y cubed dx dy, because we're trying to change the bounds of integration. And now we want to go from the smallest x value to the largest x value. And that's down here in this D1 region. So the smallest x value is on the left and the largest x value is on the right. So notice as we move from left to right, we first pass through this line x equals 1/4 y. So that's going to be our smallest x value, which I'll write as y over 4. And then our largest x value will be this line 1/3 y. So I'll write that as y over 3. So just to reiterate, here I went from left to right, so the left will be the smallest x value, the right will be the largest x value. Great, and notice both of those are in terms of y. And now I need to go from my smallest y value to my largest y value. My smallest y value is 0 because I'm down here at the origin, and my largest y value will be 3. So notice this is the horizontal line y equals 3. So here I'll do this from 0 to 3. Okay, great. So that's the D1 integral. And now let's add that to the D2 integral. So notice I'm going to write that in the same order. So I'll have 2x plus y cubed and then dx dy. But now I need to do the same thing. So if I move from left to right, I first interact with the 1 over 4 y line. So here y over 4 is the first one that I see. And the second line I see here is this vertical line, but notice this vertical line is the line x equals 1. So this is going to be x equals 1. Great. And then as far as my minimum and maximum y values, I go from y equals 3 up to y equals 4, because those are the y coordinates of this part. So I have 3 to 4. Okay, great. So we have successfully changed the order of integration. So now all we have to do is take the antiderivatives and plug the numbers in. So let's see if we can do that real quick. So notice if we take the antiderivative of this with respect to x, because that's what we want to do first, we will get, well, the integral from 0 to 3, this is the y integral, and now we'll have x squared plus xy cubed. So y is a constant, so when we take the antiderivative, it's like having a constant multiple rule. And then now we're going to evaluate this from y over 4 to y over 3, and then we have a dy integral. Great, so you would plug in, just to remind ourselves, this is x equals y over 4, and x equals y over 3. You would plug y over 3 in, you'd plug y over 4 in, and then you would find their difference. And then after doing that, you would take the y integral from 0 to 3. And then now I have, this is plus the integral from 3 to 4 of, well, it's the same antiderivative, so x squared plus xy cubed. Now I'm going to evaluate that from y over 4 up to 1 dy. So now I'll stop here with this example because I've deposited a calculus 2 type integral, which is actually pretty simple. So we'll move on to the next example. Okay, so for our next example, we're going to look at this double integral. So it's the integral from x equals 0 to 1, and then the integral of y equals 2 root x to y equals 2 root x plus 1 of the function xy plus 1 dy dx. So the y integral is happening first, it's on the inside, and the x integral is happening second, it's on the outside. So we want to change the order here. So the first thing that we want to do is draw a picture of the region and then express this thing as a double integral over that region. So let's see if we can get a nice picture drawn. Okay, so notice our x values are going to go from 0 to 1. So I'm going to put 1 way out here to give us a lot of room. Okay, great. And then now notice that at x equals 0, this thing goes through the point 0, so this bottom curve. And then at x equals 1, this thing goes through the point 2. So let's go ahead and put y equals 2 here. And notice that this bottom curve is going to go through this point right here, which is 1, 2. And then let's just remind ourselves that this bottom curve is y equals 2 root x. Okay, so we've got something like that going on right now. And then now let's look at this top curve, which is 2 times the square root of x plus 1. So now notice that's going to go through this point right here, which is 1 because it's been shifted up 1. And then it's also going to go through this point 3. So in fact, it's just this function exactly that's been shifted up 1. So we can draw this picture. And so we get something like that. Okay, and now notice that this is going to be the point 1, 3, and then we can go ahead and label this. This is 2 root x plus 1. Okay, good. Now let's go ahead and connect these 2 points, and we will shade this thing in, and we'll call this our region D. Okay, good. And now we can express this iterated integral as a double integral over this region D of our function xy plus 1 dA. Okay, great. So now we want to change the bounds of integration, which means we want to put the x bounds on the inside, and so we will be going from left to right first. But notice that the bounding curves, when you go from left to right, are changing throughout this problem. So if you look at first, from y equals 0 to 1, our leftmost curve is this y-axis, and our rightmost curve is this bottom blue line. And then here, from 1 to 2, our leftmost curve is this blue line, and our rightmost curve is this blue curve. And then from 2 to 3, we have our leftmost curve is this y equals 2 times the square root of x plus 1, and our rightmost curve is this vertical line here. So this is one where it's most definitely better to integrate it in this order, but it's a fantastic exercise to change the order of integration just to get a feel for all of these. So almost it's a better exercise because it creates a worse integral. Okay, great. So now I'm going to go ahead and label these sub regions as, we'll call this one maybe D1, we'll call this one maybe D2, and let's call this one D3. And another thing we're going to want to do is rewrite each of these functions as functions of y. So in other words, x will be written as a function of y. So notice we can do that very easily. So x in this case is going to be, let's see, y minus 1 over 2 quantity squared, right? Okay, good. And then down here, we get x is equal to, so it's going to be y over 2 squared, so that's just going to be y squared over 4. Okay, great. And we'll need that as we change this order of integration. Okay, so let's reiterate what we just said. So this is going to be the double integral over the region D1 plus the double integral over the region D2 plus the double integral over the region D3 of, I'll leave off our function and then dA. Okay, so let's do the double integral over D1 first. So we'll put xy plus 1 here, and then now we want dx dy instead of dy dx, because that's our goal, is to change the bounds of integration. So let's see, the x integral is on the inside, which means we need to go from the smallest x value to the largest x value. So in this region D1, the smallest x value is the y-axis, which is 0. And the largest x value is this blue curve, which after solving this way, we get y squared over 4. Okay, so we get something like that. And now let's see the smallest y value to the largest y value. Well, that's 0 to 1, so that's easy. So 0 to 1. Okay, great. So that's for region D1. Now let's see what we get for D2. So here we'll have the integral of xy plus 1 and then dx dy again, because we're changing the order of integration. Now let's see, we'll go from left to right again. So the smallest x value in this case will be this curve right here, y minus 1 over 2 quantity squared. So I'll write that down here. So y minus 1 over 2, actually let's just put it over 4 and then put the squared right there. And then our largest one will be this guy right here, which is y squared over 4. Good. And then notice our y values are going from 1 to 2. So 1 to 2, like that. Okay, good. Now we want to do this third region, D3. So let's see, we'll do plus. Again, it's the double integral xy plus 1 dx dy, because we're changing the order of integration. Working from left to right, our smallest x value is this curve again, which we've rewritten in this way. So this is y minus 1 squared over 4. Our largest x value is this vertical line right here, which is y equals 1. Our smallest y value is 2, and our largest is 3. So we'll go 2 to 3. Okay, so let's see what we've got. So we had this first iterated integral between these two curves. The y values were between these two curves. The x values were between these two numbers. We expressed it as a double integral over this region D. And then we took this region D and we split it into 3 regions, D1, D2, and D3, out of a necessity to change the order of integration. And then we changed the order of integration on each of those 3 regions to write them as integrals where the x part is on the inside and the y part is on the outside. Okay, great. So I won't calculate those integrals. It's actually pretty simple at this point. But what I will do is clean up the board and we'll do one more example. Okay, so for our last example, we'll look at this following iterated integral. So we've got a y integral from 0 to a third. We've got an x integral from negative, the square root of 1 minus 9y squared, to positive, the square root of 1 minus 9y squared. And then, so we obviously have the x integral on the inside and the y integral on the outside. So let's go ahead and get a feel for what this curve looks like. So notice if we set x equal to one of these, let's say the top one, 1 minus 9y squared, the square root of that, well then that's going to give us x squared equals 1 minus 9y squared, which means x squared plus 9y squared equals 1. So this is going to be an ellipse. And so notice this is an ellipse that looks the following way. So notice if the y value is 0, your x coordinates are plus and minus 1. So here we can go over here and write, here this is x equals minus 1, x equals plus 1. So we know these 2 points are on this ellipse. But then if our x value is 0, our y value will have to be plus or minus 1/3, because so we get 9y squared equals 1, so that means y squared equals 1 over 9, which means y equals plus minus third. So we get here, maybe we can write this as 1/3 to minus 1/3. Okay, so that means the graph of this is given by an ellipse, but that's not exactly what we need for this problem. So notice that this bit will be the left half of the ellipse. So let's write that maybe this way. So this blue part is x equals negative the square root of 1 minus 9y squared. Good. And then this orange part, so which I'll maybe make a bit darker, is going to be the right half of the ellipse because that's the positive part. So this is x equals positive the square root of 1 minus 9y squared. Okay, so that's what we've got going on here. And now, as far as our y values, notice our y values are going to go from 0 to 1/3. So notice that is going to be this top half of the ellipse. So our region D is given in the following way. Okay, great. So that means we can take this integral and rewrite it as the double integral over D of, well, just dA, because dx dy is just dA. Okay, now let's go ahead and change the bounds of integration. And so what we need to do in order to do that is take this and solve it for y. But that's not too bad. We'll just take this version of it at the very end to solve for y. And notice that gives us 9y squared equals 1 minus x squared, which gives us y squared equals 1 minus x squared over 9, which tells us that y equals plus minus the square root of 1 minus x squared all over 3. So we can just take the square root of 9 as 3. Okay, now let's think about this plus and minus. So the positive square root is going to be above the x-axis, and the negative square root is going to be below the x-axis. So in fact, in our setting, we don't even care about the negative part of the square root because that's going to be down here. And notice our integral told us to only worry about the upper part of this region. Okay, so now if we're wanting to change the order of integration, we will want to write this as an iterated integral of dy dx. So the y integral is on the inside. Now we look to our region and notice that the smallest y value we can have is 0. So that's just the x-axis. Great. And then the largest y value that we can have is along this upper part of the ellipse, which we have noticed is just this equation right here. So I can take this upper part of the ellipse, and instead of thinking about it written with these two pieces, I no longer need that. And I can just write it with this one piece, y as a function of x. So that means here I can write the square root of 1 minus x squared all over 3. So I've got something like that. Great. Now next what I can do is see what my smallest x value and my largest x value are, and that's negative 1 to 1. So I can go negative 1 to 1 like that. Okay, so now we can take the antiderivative with respect to y. So we have this y integral on the outside, or sorry, this x integral on the outside, which is negative 1 to 1. And now we're taking y, we're evaluating it from 0 to the square root of 1 minus x squared over 3. Now we have our dx integral like that. So that's going to give us 1/3. I can bring that out front. The integral from minus 1 to 1 of the square root of 1 minus x squared dx. All right, now there's a ton of ways to calculate this integral. I'm going to think about it geometrically. So notice the function y equals the square root of 1 minus x squared. So now we're away from this picture and we're only worried about this single integral. So this function gives you the top half of a circle of radius 1. So this is the top half of a circle of radius 1, and so we know the area of that circle of radius 1, well, that's going to be pi r squared over 2. So it's half of a circle. So in other words, pi over 2, because the radius is 1 in this case. So that makes this whole integral pi over 2, which means our final answer is pi over 6 because we have to multiply that by 1/3. Okay, this is a good place to end.